welcome to another module in this massive open online course. So today let us look at another new concept in information theory, that is the concept of mutual information. Okay, so let us look at this new concept. Okay, so this is mutual information. Okay, and as the name implies, it's the mutual information. It's what is mutual. When we talk about the term mutual, it means between two things, right? So it characterizes the interplay. It characterizes this relationship between the information of these two sources. All right. So let us consider two sources. Let's say x and y. Okay, and this is one of the fundamental quantities that can be used to analyze the performance of a communication system. All right. So I have x and y, which are two sources, or have alphabet drawn from two sources. Then the mutual information between x and y, that is denoted by I x semicolon y. Correct. This is the mutual information between x and y, that is equal to h, defined as h y minus h y given x, which is also equal to h x minus h x given y. This is the definition of the quantity. This is the definition of this term mutual information between x and y. For instance, you can have, as we are considering, our aim is to characterize the fundamental limit on the performance of a communication system. So you can have x, which are the transmitted symbols, y, which are the, so this can be, for instance, a communication channel. These are the transmitted symbols, these can be the received symbols, okay, transmitted symbols, received symbols. And basically what we have is the mutual information between x and y, okay, is equal to h of x minus h of x given y. Now look at this, we know from our joint entropy, we know that h of x comma y equals h of y plus h of x given y, which implies that h of x given y equals the joint entropy h of x comma y minus the entropy h of y. Correct? Let me write this again. So this implies that h of x given y equals the joint entropy h of x comma y minus the entropy h of y. I am going to substitute this quantity in here, and that gives me h of x minus h of x given y, which is nothing but h of x comma y minus h of y, which is equal to h of x plus h of y minus h of x comma y. Okay. So therefore this is the equivalent definition for the mutual information. All right. So I of x y is h of x plus h of y minus h of minus, that is h of x plus h of y minus hx comma y. Okay, so these are all equivalent definitions. This is also h of x minus h of x given y. This is also h of y minus h of y given x. Okay. And now, if you can look at this definition, let us look at this. So, let us look at this again in the context of communication. Now, if you look at this in the context of communication, so let us say this is our communication channel, this is y, x is what is transmitted. Now, our aim in communication is, so this is transmitted, now if you look at a communication scenario, our aim is at the receiver receive y, receive the output symbol y, output symbols y, and infer or make decisions regarding the transmitted symbol x. Alright, from y we have to infer what are the symbols x that have been transmitted. Okay. So, that is the purpose of communication. Look at the receiver, look at the outputs at the receiver, and infer about the inputs or the transmitted symbols or the inputs to the communication channel or the transmitted symbols. Alright. So, I have to infer what has been transmitted, okay, by the transmitter. Okay. Now, so therefore, if I look now at the mutual information between x comma y, the mutual information between x comma y is basically information in x, hx minus hx given y. Now, naturally, if you look at the information definition in terms of uncertainty, hx is the uncertainty in x, the uncertainty in the transmitted symbols x, hx given y is the conditional uncertainty or basically uncertainty remaining in x having observed y. So, basically hx is the uncertainty in x, hx given y, that is having observed y, what is the uncertainty that is remaining in x, right. Now, naturally, if y conveys a lot of information about x or observing y, if we are able to resolve x or if we are able to resolve x to a good degree or if we are able to estimate the transmitted symbols x to a good degree of accuracy, then the uncertainty remaining in x having observed y, that is h of x given y, must be low. Now, therefore, h of x minus h of x given y, if you look at this, h of x is the uncertainty in x, h of x given y is uncertainty in x on observing y, that is uncertainty remaining in x, you can say uncertainty remaining in x on observing y. So, h of x minus h of x given y, this whole quantity is the uncertainty about x resolved after observing y, after x that is resolved uncertainty about x resolved on observing y. Okay. So, h of x is the uncertainty in x, h of x given y is the uncertainty remaining after observing y. We expect this quantity to be less. So, h of x minus h of x given y is the uncertainty that is uncertainty about x that is resolved on observing y, or in other sense, this is the information, right, this is the information that is basically the information that has been transmitted across this is basically the information that has been conveyed across the channel, alright. So, basically Hx is the information in x, the uncertainty in x, Hx given y is the uncertainty remaining. So, the uncertainty resolved after observing y is Hx minus Hx given y, which is basically, you can think of this as the information that has been conveyed by transmission of the symbols through the channel. Alright, so that is the information, that is the mutual information Ix semicolon Ixy is the uncertainty about x that is resolved on observing y. Okay. And this therefore has a very fundamental role to play in communication. The mutual information therefore plays, as we shall see later, plays a fundamental role in characterizing the performance of a plays a fundamental role in characterizing communication across the channel. Okay. Okay. So, for a good channel, naturally one would expect I of x y to be large. I of x y to be large. That is, on observing y, one should be able to resolve x to with a high degree of accuracy. Okay, with a high degree of accuracy, or with a high degree of reliability. With a high degree of reliability, that is the aim. Okay. So, basically mutual information, as we have seen, as I have said, has a key role to play in characterizing the efficiency of communication across the channel. All right, we'll discuss this further when we look at the maximum. We'll look at the information rate across the channel. All right. Now, let us look at some properties of this mutual information. Okay. Now, the properties of mutual information are that I x comma y equals I y comma x, because we have seen this is nothing but h of x minus h of x given y, which is equal to h of y minus h of y given x, which is equal to I of y comma x. So, no surprises there. Okay. So, it is a very simple. Mutual information between x and y is the same as the mutual information between y and x. Okay. Now, also it should be clear to you, mutual information between x and y is greater than or equal to 0, because the mutual information, remember, can be written as hx plus hy minus hx comma y, and if you remember, we have seen that hx plus hy is less than or equal to hxy. We have already seen this, which implies hx plus hy minus hx plus hy is greater than or equal to hxy, hx plus hy, which implies hx plus hy minus hxy is greater than or equal to 0, and this is nothing but the mutual information. Mutual information between x comma y is greater than or equal to 0. Okay. And we can have a pictorial representation of the mutual information. This is often convenient. So, let us draw a diagram. In fact, not just mutual information, but the various measures of information that we have seen. So, let us say we have two sources. One is x, the other is y. So, this is your source x, this is y. Now, if you look at this, let me shade this with blue. This whole thing represents the information hx, and I shade in red this whole thing represents, or just to keep it simple, let me not shade these regions. So, this whole thing represents hx, this whole thing represents hy, okay, information in x, information in y. Now, if you look at these components individually, if you look at this component, this is the uncertainty remaining, this is the uncertainty remaining in x. If you look at this shaded region, that is in y but not in x, this is the uncertainty remaining in y on observing x. So, this is uncertainty in y on observing x or conditioned on x. Alright. So, we have information in x, information in y. Portion in y not in x is the uncertainty or the information in y remaining in y. Okay. So, this is basically precisely information remaining in x, that is portion, let me write it this way, portion in y but not in x. Similarly, the portion in x but not in y is the information in x on observing y, or uncertainty. So, portion in x information or x, information in x given y, okay, or uncertainty x on observing y. And if you look at this area of overlap, that is portions in both x and y, this is basically the mutual information, that is information resolved by information about x resolved on observing y, or information about y resolved on observing x. Or uncertainty in x resolved on observing y. So, we can say this is the uncertainty in x resolved on observing y. And if you look at this total quantity, now this is the joint entropy, information in x and y. This is joint entropy. If you look at both these together, this is information in x comma y. this is the joint entropy, that is information in x and y. And if you observe this figure, now you can see the joint entropy H x y is the sum of three mutually disjoint components H, this is H x given y, mutual information between x and y, and H y given x. So, the now you can write, you can see from the figure H x comma y is H x given y plus the mutual information I x y plus the information H I y H y given x. Okay, and this you can see from the figure, and this you can verify also. For instance, I x given y, this is equal to H y minus H y given x. So, substituting we have H x given y plus I x y, which is mutual information between x and y, which is H y minus H y given x plus H y given x, these cancel, these cancel, and now if you look at this H x given y plus H y, this is nothing but the joint entropy H x comma y. So, we can derive such useful results using the mutual information. Okay. So, this is the property, and you can look this. So, these are three disjoint components H x given y, the mutual information between x y, and H y given x, that is uncertainty in y on observing x. Okay. And therefore, that brings us to the end of this module. Basically, what we have seen in this module is we have defined a new measure of information, which I would say is a rather key or a rather critical measure to understand the subsequent theory that we are going to develop to characterize the fundamental rate of information transfer, that is fundamental rate at which information can be transmitted across a channel. This is termed as the mutual information. It is defined as Hx between two sources. It is defined as Hx minus Hx given y, or Hy minus Hy given x. The mutual information is already always greater than or equal to 0, and finally, we have seen the relevance of mutual information, that is the mutual information between x and y is the information about the uncertainty about x that is resolved on observing y, or you can also think of it as the uncertainty about y that is resolved on observing x. It is symmetric. Mutual information between x, y is the same as the mutual information between y and x. Okay. And it has a fundamental role to play in characterizing the rate, or how much information, that is at what rate can information be transmitted across the channel. Okay. And further, we have seen a pictorial way to sort of comprehensively represent the various quantities that we have seen so far, the entropies, the joint entropy, the conditional entropy, and now also the mutual information between two sources. Alright. So, we will stop here and continue with other aspects in the subsequent module.